Hello everyone. So today we're going to go over section 4.5 and 4.6, exploring combinations. So here we have example number 1. 5 sprinters compete in a race final. So we're looking at how many ways the medals for first, second, and third place can be awarded. So 5 different sprinters can win first place. After that, the 4 remaining sprinters can win second place. And finally, there are 3 different sprinters that can win third place. So if we multiply those 3 numbers together, we'll get 60 ways that the medals can be awarded. Now, from the previous sections, we also know that this is simply NPR, where n is equal to 5 and r is equal to 3. So we have 5 factorial divided by 5 minus 3 factorial, or just 5 factorial divided by 2 factorial, which also gives 60 ways. Now, suppose instead that the 5 sprinters were competing in a qualifying heat, then all that matters is whether the sprinters qualify or not. And in this case, the first 3 sprinters qualify for the next round. So again, we have our 5 sprinters here. And they either qualify or do not qualify. So there are 3 Qs for qualified sprinters and 2 Ds for did not qualify. In other words, we're just looking at the arrangements of these 3 Qs and 2 Ds. And once again, as we saw from before, this is a question about the permutations of repeating objects. So we have 5 factorial divided by 3 factorial for the 3 Qs times 2 factorial for the 2 Ds. And here we can expand the numerator, 5 times 4 times 3 factorial. And of course, the 3 factorials will eliminate each other. So here we simply have 20 divided by 2, which means there are 10 different ways that the sprinters can qualify for the next round. And this example highlights the difference between combinations and permutations. In the first case, where there are medals to be awarded, first, second, and third place, that is a permutation question because the arrangement of first, second, and third matters. And in the second part, we are looking at a combination question where we are just selecting the qualifiers and the order that they come in do not matter. Let's look at a second example, example number 2. So 3 students from a class of 10 are to be chosen to go on a school trip. In how many ways can they be selected? So again, we have 10 students, 1 through 10, and there are 3 S's for selected and 7 N's for not selected. And this right here is only one of the possible arrangements. To find the total number of arrangements, we are having 10 factorial, so for the 10 students, divided by 3 factorial for the 3 selected students, and then 10 minus 3 for the 7 students who are not selected to go on the school trip. We can simplify that as well, so 10 factorial over 3 factorial times 7 factorial. And using a calculator, we can find that this will be 120 ways that the students can be selected. Next, we can generalize this result, combination of n different objects taken r at a time. So right here, NCR, usually read as N choose R. Some textbook uses this parenthesis and then N over R notation here. And expanded, we have N factorial over R factorial times N minus R factorial. Note that by comparison, the permutation formula is just N factorial over N minus R factorial. Okay. So one more to look at a quick example using the formula. 16 students, 4 of which are going to be selected for a survey. So this is a combination question because the order in which the 4 students are selected do not matter. So this is just 16, choose 4. Then we apply the formula 16 factorial divided by 4 factorial times 16 minus 4 factorial, which can be simplified to just 16 factorial over 4 factorial times 12 factorial. And using a calculator, this is 1,820 ways that 4 students can be selected out of 16. So the next step is to add in other components from previous sections to work with more sophisticated combination problems. First thing we're going to do is add the fundamental counting principle. So in example 3, we are looking at an athletics council with 15 council members, and we're trying to form a subcommittee with 7 council members. So in the 15 council members, 9 of them play a single sport, and there are 6 who play multiple sports. The subcommittee must consist of exactly 3 students who play multiple sports. Now the first thing we're going to look at is if there are 7 people in the subcommittee, we're going to subtract the 3 that need to be multi-sport students. So we have 4 spots left for single sport students. Oh, doesn't say that this, oh. Sorry about that. Okay, so we have 6 students who play multiple sports. We're going to choose 3 of them. And then there are 9 students who play a single sport, and we need to choose 4 of them. Now, by the fundamental counting principle, if there are A ways of doing something and then B ways of doing a second thing, there are A times B ways to doing both of those things. And here we are looking at selecting 3 multiple sports students out of the 6, and then 4 single sports students out of the 9. So we're going to multiply them together afterwards. Let's go ahead and label this. This is the multiple sport or multi-sport. And here we have the single sport. Here, if we were to use a calculator, 6 choose 3 will be 20, and then 9 choose 4 is 126, and if we multiply those two numbers together, there are 2,520 possible subcommittees. So next question is very similar. There are 5 guards, from which 2 are chosen to start, there are 7 forwards, 3 of which are chosen to start. And then, so 5 choose 2 is 10. 7 choose 3 is 35. Again, just using a calculator. Or we can expand and solve algebraically. But either way, 10 times 35 is 350. And these are possible starting lineups. Now, in addition to the fundamental counting principle, we can also add cases to make even more sophisticated combination problems. So let's look at example number 4. Planning committee is to be formed for a Earth Day program. 13 volunteers, 8 teachers, and 5 students. And we're looking at 4-person committee that has at least 1 teacher. So there are a few different ways of doing this. So either we have 1 teacher, and of course 3 students. And we also have, so this is 1 teacher. Next we have 8 choose 2 for 2 teachers, and then 5 choose 2 for the 2 students. After that, we have 3 teachers out of the 4 spots. And 1 student. And finally, all 4 committee members can be teachers. So we have 8 choose 4 times 5 choose 0. Once all 4 of these cases are listed, we can evaluate each one individually. So 8 choose 1 times 5 choose 3 is 80. Followed by 8 choose 2 times 5 choose 2, which is 280. From there, 8 choose 3 times 5 choose 1 is actually 280 as well. And finally, 8 choose 4 and then 5 choose 0 gives us 70. Now, once we add all 4 of these numbers together, we can see that there are 710 ways to form the committee. Another way of thinking about this question, which is quicker, is to consider what is the opposite of the statement that's given. So here it says at least 1 teacher. The opposite is if there are no teachers. Now, which means we can do the following. We have 13 people, volunteers, and then we're going to choose 4 of them. Now, what this is that we are forming committees as though there are no restrictions. So this is going to be all the possible committees, and we're going to subtract the possibilities that contain no teachers. So that would be 8 choose 0 times 5 choose 4. From there, we can see that 13 choose 4, so that's the no restriction case, will give us 715 different committees. And there are only 5 committees with no teachers. So subtract 5. And we can see that we get the same result as before, and that is 710 ways to form the committee that has at least one teacher. Let's look at one more short example here. We are showing 5 movies. There are 14 available, 10 animations and 4 comedies. So we're looking for schedules that include at least 4 animations. So we can either have 4 animations, in which case we have 1 comedy, and then the case where all 5 movies are animations, and then there are no comedies. And again, just like before, using a calculator, 10 choose 4 times 4 choose 1 is 840. And then 10 choose 5 times 4 choose 0 is 252. So there are 1,092 possible schedules. So today we covered the difference between permutations and combinations. We looked at the combination formula, consider using combinations along with fundamental counting principle, and finally we'll look at what happens when there are combination problems involving cases. And that's it. So that's it for today. Once again, thank you for listening.